Thank you for having me. Did you know that a 2-second delay in a voice agent can cause a decrease of trust and usability of your application of about like 50%? That basically means that half of the people that use your application is basically hating it. So today I'm going to talk about how to have and to build a voice AI solution. And I will touch in key topics like WebRTC, open source, and small language models. My name is Alberto Gonzalez. I'm the CTO at WebRTC Ventures, and we specialize in building these kind of applications, but in general, voice and audio live applications. So let's dive in. I will briefly do an introduction of real-time voice AI. I will talk about some typical architectures to build these kind of applications, how to optimize prompts, and how to use small language models, and also I will share some benchmarks that I ran on my end on like what's the typical latency you see, and compare different providers. And yeah, finally I will have a live demo. So I will skim through that, but yeah, basically there are some stats about some obviously industries getting into voice AI. Particularly, we have seen healthcare. We have been working with some companies doing customer service for healthcare, and that we see is like the main use case, at least for B2B. You can see, for example, some reports that say that customer service voice AI customer service would grow like 10x in the next 7 years, and it makes sense since like it kind of upgrades the current IVR functionalities to something a bit smarter that can handle a bit more complex actions. And education and entertainment, that one seems that it's pretty popular. It's not that much what we do, but it seems the one that has the largest market of voice AI. But yeah, there are some challenges when building real-time voice AI. The first one is latency. It has different modules where the audio goes through, obviously like the transmission of the audio, but also processing of like transcription, then inference through an LLM, text-to-speech, voice detection. There are many pieces, and all of them add up quickly. Also, there is the resource intensive of large language models, which is also a challenge, and the rapid evolution of everything, basically. Like there were tools, large language models we were using last year that today are kind of outdated, or transcription models that also have been improving a lot in the last few months. So you need to keep up all the time with all of this. And the last one is the error propagation. With LLMs is a bit easier because it's text-to-text, so there is no conversion here, but if you're doing the transcription, there can be some errors in the transcription that error propagates to the LLM, and the response obviously adds, like it kind of also adds up and degrades. And why WebRTC is a good transport for this in some situations? Well, as you know, all of you here, it's widely supported. It's used for communications, and as Anthony was saying today, this morning, like developers now, all developers are going to become communication developers, and that's what is happening. No, like WebRTC is allowing every developer to send audio to not just humans, but can be used for sending it to agents. It's built for low latency, and it has some benefits, like it can adapt to network conditions that we have, for example, in this room. So if there is some low bandwidth, WebRTC can handle those situations better than other transports. But yeah, WebRTC is not the only solution, and we have been hearing about it a lot from the guys from, for example, Asterisk. Like there is a very common approach that is just use WebSockets. And here I just show a quick diagram of when does or does not make sense to use WebRTC for a real-time voice AI solution. And I think the main question is where is captured, and if this audio is going to go through the public internet. If it's captured locally on a web app and processed there, there is no need probably to use WebRTC. But if it needs to go through the public internet, in that case is when you can leverage the benefits of WebRTC for transmission of media. And here, yeah, I explain like kind of the logic how it could be done and followed. And this is just an example of why, for example, it's not a good idea to use WebSockets to send audio over the public internet for a voice AI agent. This is just from an open source project that just did a test of in a simulation where you simulate like 15% packet error loss. And you can see the blue line is the transmission of large amounts of data, and the latency you can see is close to 4 seconds, while over WebRTC is close to 3. So it's you are adding more than 1 second actually of latency by using WebSockets. The reason is because there is a lot of packet error loss in this network, so there are retransmissions, and yeah, I think this kind of clearly explains a good example of why it would make sense to use WebRTC over public networks for not just for video calls, but also for conversations with voice agents in real time. And there are some typical architectures to do that. This, I will call it the traditional architecture. It's kind of involves 4 modules. So there is the voice audio detection piece in charge of knowing when the audio that is coming in is a speech. And then once we detect that, we start and do the speech-to-text processing. Then that text is sent to the LLM. And after that, the response from the large language model back as a speech using also another model that I call here like a text-to-speech model. This is how some open source tools or frameworks handle this. And there is obviously a more modern architecture for voice AI, and probably you have heard about OpenAI real-time API. So this is a little bit more like how it looks for them, where it's just like a direct multimodal solution. It's less modular, so that means you don't have control over which text-to-speech model you use or speech-to-text model you use. It's kind of all built inside the system. And how this works, and I'm not that data scientist, so it's kind of a topic I won't get into, but basically use spectrograms to understand the speech that's being said. And actually, you can keep the tone of, you can understand the tone of what is being said, something that actually is lost when you use the traditional pipeline. If you are doing a transcription, you don't know if the person was screaming, was crying. That's lost completely. So these models actually have this benefit of having that. But yeah, the challenge today is in terms of cost. These models are a bit like more expensive to run, and are more complex. And to add on, like I mentioned, these kind of two types of architectures, and you can build them using open source. I think that's a very acceptable approach. Yeah, like you could have your whole stack built on open source, and we have done that ourselves. I don't need probably to explain it in this room, but obviously it has a lot of benefits, flexibility, transparency, community, all that. And some popular tools we have used for real-time voice AI to do that, and I will show the demo later that use some of these, are Pipecat or LiveKit agents. Those are some open source frameworks you can use to orchestrate agents. I know also SignalWire agents have one that I still need to experiment. But yeah, you can use that to decide which models to use. No, like if I want to use, for example, Pipecat, and I want to use Whisper for the transcription, and I want to use Kokoro for text-to-speech, you can decide. That's, I think, the power of using this kind of orchestrators. But yeah, I wanted to touch on two important points, not just the architecture in a high level, but there are some things to do that are important as well. One is optimizing the prompts. So this is might sound a bit obvious, but prioritize for short responses, because actual large language models, they are much faster processing inputs than outputs. So if you send them a long input, actually it's not that big of a deal. But to send back outputs, that's because of how they are built, like they will be much slower. So that's how you want to configure the prompts for. Also for relevance, of course. So what you write first, it's generally more important for the large language model. And you can also leverage structured inputs or special tokens. So large language models, when they receive a prompt, they have a pre-processing step where they structure it internally and create, like, add special tokens. You can do that in advance, for example, using regex, and you could structure it in a way that, like in this example, you add those brackets about who is the speaker. You can add information that adds, for example, the urgency information, stuff like that. And the other important topic I wanted to cover is small language models, and probably you have heard about it. It's basically large language models that have less parameters. And I think it's perfectly fit for real-time voice AI. They are much cheaper, like cost-efficient, faster processing, and they can run even on edge devices. So you can run a 7 billion parameter or 1 billion parameter on your laptop, and I will show it today. And you can also run it on the server, and also will return with lower latency. It has the challenges of accuracy, of course, but there are use cases where you don't want to go over, like, broad, deep reasoning conversations. Like, you don't need a PhD in mathematics to basically answer a call or redirect a call, or let a user know how to perform a purchase or a refund. And another things that are usually done with small language models is the parallel agentic execution. So you can have different voice agents answering at the same time if you want, and just picking the part that you are interested in. So the small language model, for example, can respond something like, sure, let me answer this, or sure, I can help you with that, and then have the large language model handle more complex actions. And the other typical use case is the turn detection. So if I'm talking and I'm not finishing the sentence, it's going to understand that it's not finished. So that's how this small language model would know that it's not completed yet, and it will keep transcribing and not sending it to the LLM. And here I have some, I wanted to touch on benchmarking, and I'm a bit short in time for that, but I will just skim through that. There are three main things that we look at when we test this, and I will focus today more on latency. I think accuracy could be a whole different presentation, like a complete one. But we have used something called Coval that lets you see what was said. And you can use something called LLM as a judge to evaluate what was said. So you can, instead of having just people say, like, was this conversation correct? You are telling the LLM to review if the conversation was as expected, and if there is something else we should tweak on the prompt to make it more aligned with our goals. And then there are the old school surveys, and I think those are still pretty useful to know a bit about the agent performance. And this is kind of the whole flow sequence of an example, in this case, 1.6 seconds, glass to glass, in this case, voice to voice, that basically counts the time I stop speaking, so it's the end of sentence or my question or whatever I said, and the time I start hearing the first byte of audio back from the agent. That would be the 1.6 in this example. And there are all these different steps that I was mentioning, no? Voice audio detection. It takes some time to detect, and that's what you can tweak, no? Like you can say, do we wait 100 milliseconds until we decide this is a speech, or we want 200, or, you know, like the more we wait, the more accurate it is, but the slower it is. So it's kind of a balance here of what makes sense for your use case. And here I did some benchmarks, like baseline runs on my laptop, so it's obviously not a research paper. You can try yourself, but there is a huge difference comparing different providers and different combinations. I was quite surprised, for example, OpenAI GPT-4o performs really bad for text-to-speech, actually. But then when we use the real-time one, it was, in this example, getting an average of 1.4 seconds. Also, again, like this is the real latency, counting everything, transmission of audio, like the whole process, not trying to simulate some parts of the pipeline. And there are some things that you can do to improve that. No, like we reached 1.3 seconds in that example, but you can reduce that further if you collocate the services next to you. Because here I'm using third party. In those benchmarks, I was using third parties that are located somewhere in the US. There is a round trip latency that can be 100 to 200 milliseconds. So basically having those services in your same infrastructure that can reduce and reach sub-second latencies. And now I'm going to show a quick demo of first a voice agent kind of optimized using third-party services, and then one running locally on the device. I'm sorry about the demo. If someone wants to see it, I have like a voice agent that runs. There are two types. One using like third-party services, like Grok, Whisper, and so on. And then there is another version that I can run locally that is using all open source. And again, what I was saying is using Whisper locally, Llama, 1 billion parameters locally, and Kokoro, which is a text-to-speech, also open source. It does it runs on CPU, so that's actually pretty cool. And I have, I think it's voice AI is ready actually for prime time. Like we have used it already in projects. It's interesting if you can try also with small language models. Of course, be realistic. It's not going to handle everything at once, but for specific use cases, it works. And there is this demo that I have there on GitHub. You can try it out. It has also, it's plugged in with Prometheus, Grafana, so you can also see the latencies you get from from using different models. And yep, that's it. Thank you so much.
Thank you, Alberto.